Today, we get to look at the easiest derivative rule, even easier than the constant. Okay? Derivative of a constant is 0. Alright? Even easier than that, though, is our exponential function. Okay? The last 3 days of our unit here that we're looking at, or the last 3 lessons, I should say, we're going to be looking at exponential functions, logarithmic functions, and then finally trig functions. Okay? All of the other stuff we've already learned, product rule, quotient rule, chain rule, all applies to each of these. Okay? This one, though, is actually really easy. So I wanted to start by reviewing real quickly what we know about the function e to the x. Okay? E to the x is our exponential function. Remember, e is the number 2.718 and so on, the irrational number. We know that the graph always passes through the point 0, 1, okay, because e to the 0 power is 1. We also know that there is a horizontal asymptote right here on the x-axis. Okay? So when will an exponential function equal 0? Never. Okay? We have an asymptote at 0. Okay? So that's going to be, remember what we were just doing where we found a derivative and then we said, when does this equal 0? If you have an exponential part of your derivative, that will never equal 0. Okay, and we'll see that later. Then also notice it's going to be increasing unless we were to make this, say, a negative x, then it would be decreasing. That would be our decay, exponential decay. But that's getting into stuff we're going to need to use the chain rule for. Okay? But this really, really easy rule is this. Okay? The derivative of an exponential function, e to the x, is e to the x. Okay? The derivative with respect to x of e to the x is e to the x. Okay? I told you this was the easiest rule.
So it's just exactly what the
It's exactly what it is. Okay? Well, the cool thing is that, it's really easy to find. What we are going to find out, though, is that we're going to have this exponential function within other functions, or we might have other functions inside the exponential. Okay? So we're going to be using the chain rule. Or we might have to use the product rule or the quotient rule. And that's what I want to spend our time today looking at, are a few examples of those types of functions. Okay? So, here we have kind of taking this one step further and illustrating our chain rule. Notice here, derivative of e to the x is e to the x. If e has another function in the exponent, that's a case where we have to use our chain rule. So notice the derivative of e to a power is e to the power, so that's the outer function. But then we have to multiply by the derivative of the inner function. So it's e to the f of x times f prime of x. Okay? Does that make sense? All right. Now, by the way, another way you might see this, you might see people write this as e to the u. The derivative with respect to x of e to the u would be e to the u times u prime. That's another way you might see people write that. Okay? So here we have an example. We have 2e to the x plus e to the negative 3x. Okay? So first of all, we just have a constant multiple of e to the x. 2e to the x. So what's the derivative of 2e to the x? It's just, what'd you say? It's just 2e to the x. Remember, a constant multiple, you just take the derivative. So what's the derivative of e to the x? It's e to the x. And then you multiply that by the constant. So it's just 2 to e to the x. Okay? Now, the second part, you'll notice we have a function in the exponent, this function of negative 3x.
So it's e to the negative 3x times 0.
Not times 0, times
Negative.
negative 3, okay? So good. The derivative of e to a power is e to the power. So that's why we have the e to the negative 3x. But then we have to use our chain rule. This is the chain rule part right here. The derivative of the outer function is e to the power. Then we have to take the derivative of that power. So in this case, it's negative 3.
So do we write it out first as it was already, right? With e to the negative 3x, we wasn't writing the function, so we write it out first. And then we take the chain rule of the exponent, right?
That's correct. Good. Okay, so we could rewrite this 2e to the x minus 3 over e to the 3x, if you want. Okay. One of the things when we're dealing with these exponential functions, it's actually not uncommon to go ahead and leave the negative exponents. I know we've been simplifying all of our negative exponents. It's not uncommon to just leave it as a negative exponent in these cases because we have the exponential decay functions. We're used to seeing that negative exponent just indicating an exponential decay. So you could write it like this, or I don't care if you would leave it like 2e to the x minus 3e to the negative 3x. Okay, either of these would be acceptable. Okay, this is kind of an exception to that always simplify negative exponents rule. Okay, let's try a couple others. We've got the chain rule, or where we've got the product rule and the chain rule, or the quotient rule and the chain rule. All right, let's start with our product rule. It's been a few days since we've done this, so what is our product rule?
B prime times B plus B prime times U. Did I just say something?
Yeah.
Lodi high.
That's quotient rule.
Oh.
Product rule, u prime v plus uv prime. Okay. So,
So will the x squared be u and the e to the negative x will be v?
that's correct. Okay. This is our u, and this is our v. Okay. So u prime equals 2x. What's our v prime?
E negative x times negative 1.
There you go, good. E to the negative x, the derivative of the outer function is e to a power, so it's just e to a power. But then you have to use chain rule, so it's times the derivative of negative x, which is negative 1.
Should we rewrite it as negative e to the negative x?
Yeah, that'll help simplifying stuff. Okay. Now it's just like our other ones, you're just plugging it into our product rule. dy dx is u prime times v plus u times v prime. Okay? What happened before anytime we had the chain rule inside the product rule?
Take it out.
We had a common factor we could take out. Well, look, that happens here as well. We have common factors of x and e to the negative x. Okay? So if you look at what's left over, we have a 2, and we have the negative, and we have the other x. So 2 minus x is left over. Alright? That's not too bad.
No.
Now, think back to what we were doing in the IP. If I wanted to see where this equaled 0, okay, where is this, what x's are going to make this equal 0?
2.
2 and
0.
0. Okay? I get the 2 from this factor, I get the 0 from this factor. This factor,
Would it be 1? Or negative 1? Is it e to the
no.
e to 1?
When is e to a power going to be 0?
It's not, never yet.
Never, because
It's an exponential.
the exponential has an
Asymptote.
asymptote, okay? So, just keep that in mind here. This will never equal 0, but we get 0 and 2 as 2 points where our derivative will equal 0. Okay?
That's a connection.
Yep, it is. Good. Good. Alright, now let's check out the quotient rule. Okay, you guys have just been working with this, so it's u prime v minus uv prime all over v squared. Okay? So what's our u prime? The derivative of e to the 2x.
2 e to the 2x.
Good. 2e to the 2x. Derivative of e to a power is e to that power, so that's where the e to the 2x comes from. Then we have to multiply by the derivative of 2x.
2.
So that's 2. Good. What's v prime?
1.
That's nice. Alright. So, dy dx. Again, we had the chain rule inside our quotient rule, so we're probably going to have a common factor, right? So, we've got u prime, which was 2e to the 2x, times v, minus u times v prime, all over v squared. Okay? And what do you know? We do have a common factor, e to the 2x times 2x minus 1 all over x squared. So now if I were trying to see where this equaled 0, this is never going to equal 0, but 2x minus 1 equals 0 when x is a half. Okay? So now hopefully we're kind of seeing why we would simplify some of the ways we've been simplifying, pulling out those common factors and stuff. Okay? Any questions so far?
I like the quotient rule because it doesn't ever look like you're done. Like that doesn't look like the answer, you know? Like, you know when you get something
Just keep going.
and you're just like this isn't right. Like the quotient rule never feels right. I feel like I should keep doing stuff with it.
It doesn't turn out real pretty or
Yeah.
anything, you know.
It's not nice to look at.
So, well, it'll be useful though. So,
I'm sure.
all right, let me resize that. Okay. All right. Here's a couple others with the chain rule. We've done the chain rule. This is a little bit of another step of complexity here. We've done the chain rule where we have the function inside the exponential. Now we've got the exponential as part of the inner function. Okay? So let's take a closer look at these. Okay? The inner function in this case is the e to the x minus 1. Okay?
So it's a chain within a chain. Is it going to be 3 times e to the x minus 1 to the second power times ex?
Okay, good. Yeah, dy dx. The outer function is something cubed, right? So the derivative of something cubed is 3 something squared. Okay?
But those ex stay the same, right?
Yes, the derivative of the inside
Oh, I see.
is e to the x plus 0, so just e to the x. Okay?
Do we simplify? Do we multiply by ex by 3?
Yeah, you might want to rearrange it just so it looks a little nicer there. 3 e to the x times e to the x minus 1 squared. It's not wrong to leave it, but
Still not kidding.
Like that's it. That's your answer.
that's it. That's your answer. Now, this one actually, you'll notice there is a point where this does give us 0. Okay? The e to the x will never equal 0, but this,
Oh yeah, e to 0.
when x is 0, e to the 0 would be 1, and 1 minus 1 would be 0. So in this case, even though there's an e to the x in there, don't automatically just dismiss it, you know, if you're trying to set the derivative equal to 0.
Wait, so why are you saying that? Why are we looking that it can be 0 at any point?
I'm just kind of, remember, we're trying to just I'm just trying to preview what we're going to do in the future, setting these equal to 0 and finding those values of x. This, because of the asymptote, will never equal 0. This, though, to make the whole parentheses 0, the e to the x would have to equal 1.
Okay, so we can have it equal to 0. Like, we would make it equal to 0, right? And
Yeah.
we'll have to find the x.
Mm-hmm. Yeah. So you'd have to think, all right, e to what power would be positive 1? Well, that would have to be e to the 0. So x equals 0 would make our whole derivative 0. Okay. We'll do that specifically later. I'm just kind of throwing it in now just so we kind of get
So
comfortable with it a little bit. All right, here's another one. This one's kind of fun. All right. How would you guys take the derivative of this?
At first, raise it to a negative a
Okay, could we use the quotient rule?
half. Yeah.
Sure. But anytime you have 1 over, or just any constant over something, I would just rewrite it as the negative exponent, because it's easier to do chain rule than it is to do quotient rule, right? And if you've got a constant up there, what's your u prime going to equal? 0. Okay? So, yes, good. We're going to rewrite this as 2e to the negative x plus 1 to the negative 1/2 power. Okay?
So that means the derivative will be negative half multiplied by 2e raised to the negative x plus 1 raised to the negative 3x
Very good. Okay.
Times 2e to the negative x times negative 1.
Yes. That's good. You see what we just did there?
Wait, but do we leave 2e to the negative x even though it's not the... Like, we can leave only if it's a quotient, but if only if it's like 2e to the x power.
But yeah, would we make it a negative 2 to the ex or?
Well, we will. We will. I just wanted to lay it out like this, because what she just did is exactly what we need to do. Alright? This is like inception calculus. We're doing the chain rule inside the chain rule. Okay? We've got this that we have to take the derivative of, because that's the inner function, right? Well, the derivative of 2e to the negative x plus 1, we're trying to take the derivative of this inner function, but it has an inner function as well. Okay? So the derivative there is 2e to the negative x, but then I have to multiply that by the derivative of negative x. That's where that negative 1 is coming from. Okay? So I have a function within a function that's within a bigger function. Okay? The negative x is inside my exponential function. The exponential function is inside my radical function. Okay? So that's where this is coming from here.
Wait, where do you get the negative 1 from?
From, when I do the derivative of this inner function,
Yeah.
okay, that right there is a function inside this function.
Okay.
So the derivative of all of this is
Okay.
2e to the negative x, but I got to multiply by the derivative of
Because the
that.
derivative of negative x,
Yeah.
okay.
Okay, so it gets a little complicated here. All right. The nice thing is this one simplifies pretty nicely. Okay, we've got the negative 1/2 actually will cancel out the negative 2. So this whole thing will simplify down to just e to the negative x times 2e to the negative x plus 1 to the negative 3/2 power. And if you'd like, you can write this whole thing as 1 over e to the x 2e to the negative x plus 1 to the 3/2 power. Okay.
So how can we take out e to the negative x if we have negative, like 1/2, negative 3 over 2 on top? Like,
I'm not taking out and I'm not taking anything out. The only thing I'm doing here is I have a negative 1/2 times a negative 2. So negative 2 times negative 1/2 is just 1. So that's why that canceled out. Mm-hmm.
When you say to simplify, do we have to also simplify the 2e to the negative x? Like, would we have to do like 2 over e to the x? Or
No. No, this is like what I was saying. When we're dealing with e to a power, honestly, I mean, with this one, this would be good to simplify, put that in there. But like anytime you have e to a negative power, you don't have to simplify that if you don't want. The only time you might is if it was another show problem they give you. Sam?
I'm sorry, how did you get the negative 1/2? Like, why does that solely apply to the second parentheses? Like, why couldn't you cancel out? I thought you guys like distribute through.
Well, we can't distribute because this is raised to a power here, right?
Okay.
But also, this is all just multiplication. So I'm just putting stuff together at this point. Okay? I've got a minus 2e to the negative x. If you want, we can it would be negative 1/2 times, if I pull this factor at the end up to the front, it would be times a negative 2e to the negative x, which there's no plus sign in there, so I'm not going to distribute, I'm just multiplying there, times 2e to the negative x plus 1 to the negative 3/2. Okay?
Okay, so I guess you can just only do stuff with the first one.
Yeah, you can because it's multiplication, it's not addition.
Gotcha. And then you just take out the e to the negative x and you're home free basically.
Yeah, this is what ended up right here, and then this was just what's left there.
Gotcha.
Okay.
I'm sorry, one last thing.
Mhm.
How did you just take the e to the negative x out of the second parentheses and had it not?
I didn't take it out. It was already here.
Okay.
It was already here. Yeah, I didn't factor anything out there. That's all that was left.
Okay, thank you.
Okay. All right. So that's the idea here with our chain rule. We have functions within functions and all of that. So it gets kind of interesting, all right? Now, with this only applies to e to the x. Obviously, there are exponentials that have other bases. I'm going to show it to you just briefly here. This goes beyond what the IB requires you to know, but I figured I'd show it to you anyways. All right. if I have a different base, okay, basically what I can do is I can use the change of base formula, okay, in that kind of an idea. Notice here, if I have y equals b to the x, then our derivative is going to be the natural log of the original base times b to the x. Okay? So, if I'm going to take the derivative of y equals 5 to the x, the derivative with respect to x is just going to be the natural log of 5 times 5 to the x. Okay?
That's it? That's the.
That's it.
Oh, yeah. Do we need to simplify it anymore or no?
Nope, that's it.
So the second one would be ln 10 times 10 to x.
Yep, ln of 10 times 10 to the x. And what about this last one?
Can we have negative, ln negative?
Very good. Okay. If you tried to use this rule, ln of negative 10 times negative 10 to the x, this is undefined.
Because it's a negative number.
Yeah, remember the domain for the log function is that the argument has to be greater than 0. Because these log functions look like this. And there's an asymptote at x equals 0. So, the derivative is undefined for that function. That function's not differentiable, we would say. Okay? So, kind of a cool little rule. But again, that's kind of beyond what you have to be able to do for IB.